Hello everyone, I'm Shija from University College London. Today we are here to present our paper, Understanding the Quality of Body Movement by Leveraging Wi-Fi Sensing. So talking about the quality of body movement, we want to start by an example. Chronic pain limits the daily physical activity of sufferers. Those with chronic pain often display protective behavior in their routine tasks. For example, a sit-to-stand behavior, individual with chronic pain might exhibit signals like rigidity, stiffness, or hesitation, or showing a fear of movement or reliance on a chair for support while standing up. Such protective behavior are examples of the quality of body movement. The popularity of wearable and mobile sensing devices have given rise to an increasing interest in complex sensing applications. For example, user activity recognition. By leveraging the existing low-cost sensors, including optical sensors such as RGB cameras or depth RGB, or wearable sensors of accelerometer, gyroscope, and we're now able to track a wide range of human behaviors. However, these sensors are considered as intrusive sensing. For example, camera require line-of-sight environments, limited coverage, occlusion issues, or raise privacy concerns. And meanwhile, wearable sensors require users to simply wearing them all the time, may limiting users' physical movement in their daily lives. Hence, we are looking for a passive and ambient sensing method. These bring us to wireless sensing, such as Wi-Fi signals. Wireless sensors are considered as passive and ambient sensing. It can work under non-line-of-sight condition. It has the advantages such as through-the-wall, larger coverage, device-free, with less privacy concern features. So how does Wi-Fi sensing works? Wi-Fi radio are transmitted between Wi-Fi routers and receive devices. So when a person moves, this causes the radio waves to absorb, reflect, and interfere in different ways. These change the signal propagation signatures, and such variation signatures can hence to be used to map different body movements and signal variations. So current application including using CSI, the channel state information extracted from Wi-Fi routers for physical activity recognition, such as walking, sitting, and standing. And meanwhile, Premier work used the antennas located close to the chest to capture chest movement and then extracted the Wi-Fi signal variations altered by inhale and exhale movements, indicating the respiration rate. And very limited prior work has been explored on leveraging Wi-Fi for effective computing. One work we found is using radio frequency signal to capture the chest movement to extract the heartbeat and respiration signal, and then mapping these two signal features with 4 categories of emotion, which including joy, pleasure, sadness, and anger. Indeed, we have witnessed Wi-Fi sensing becomes an emerging research area. However, previous studies have only focused on detecting different types of activities, such as walking, standing, falling down, chest movement that related to physiological information. There is still little understanding on how Wi-Fi signals can be used for assessing quality of body movements that related to our affective status. For example, the quality of the body movement. To answer this, can we use Wi-Fi to detect the quality of body movement? So in this research, we focus on detecting the protective behaviors. To answer this question, we divide the research into 3 parts. Construct a Wi-Fi sensing system to capture body movement. And secondly, collect datasets containing different body movements that related to protective behaviors. And thirdly, develop recognition algorithms to identify protective behaviors. We developed a round-trip Wi-Fi sensing system. This figure illustrates the layout of our Wi-Fi system in a room. The layout consists of 4 Wi-Fi devices placed in the 4 corners of the room respectively. The participants perform in the center of the activity of interest within the space enclosed by the sensor layout. In terms of the so-called round-trip Wi-Fi CSI sensing system, we developed the system based on the open-sourced Nexmon CSI2. So each router performs as both signal transmitter and receiver, that it receives the CSI signal from the previous router and then transmitted the signal to the next router from AP0 to AP3 as a round trip. So there are 4 activity types. Level 1 from the top, illustrated in this figure, performed by the participants. So it includes sit-to-stand, stand-to-sit, reach and grab, and bend and pick. The sit-to-stand and stand-to-sit movements were further performed as normal or with left and right asymmetries as level 2. And third, each activity and the different symmetric variants was done in 3 different speeds: fast, normal, and slow. We collected the denoise 4-channel Wi-Fi CSI dataset, which contains the data collected from 16 participants of 5 activities, with each movement repeats for 3 to 5 times. And here is a demo video. Figure shows example of amplitude and phase information, highlighting distinction in the signal pattern for sit-to-stand and its literal asymmetry variants, bend and pick and reach and grab movements for the same participant. We present a novel hybrid fusion stacked LSTM architecture, which is illustrated in this figure. The use of LSTM to encode temporal relationship is well established in the area of machine learning, so it was an intuitive building block for our model. Our stack LSTM fused 2 LSTM networks. The first LSTM network captures mid-level information about the type of activity encoded in the signal. We pre-trained this model by feeding the amplitude and phase information extracted from the CII with a ground truth label of 4 different physical activities, including sit-to-stand, stand-to-sit, picking, and forward grabbing. The hybrid LSTM here highlighted is used for detecting protective behavior, so in this model, we add another LSTM network, the LSTM2, as a parallel feature extractor that extracts the information while aiming for understanding the interplay between the rich CSI information and the protect behavior features. So in this architecture, the LSTM1 layer, which is transferred from the pre-trained model, is frozen during training, and multi-layer perceptron are added to connect the latent features extracted from these 2 LSTM subcomponents then used to map with protective behavior in terms of lateral asymmetry and movement speed level. Here is the result of F1 score of our model over all participants. For identifying the activities, it shows an average accuracy of 84%, while compared to those shallow machine learning algorithms such as SVM, KNN, MLP that have poor performance lower than approximately 40%. And regarding detecting the protective behavior in terms of detecting the lateral asymmetry, our hybrid LSTM model shows 90% accuracy, while the shallow algorithms only obtain around 50% accuracy. While the speed level detection, it achieves the performance of 92%, while shallow algorithms only have about 30% accuracy. And this figure shows the confusion matrix among 3 types of recognition tasks. Our hybrid LSTM model shows an overall 92.3% accuracy among all classes. To conclude, our work is the first to use Wi-Fi signal for assessing quality of movements that related to pain behavior affective status. We first construct a novel hybrid fusion static LSTM network for assessment of Wi-Fi-based protective behaviors, and then we evaluate the system on automatic detection of activity types lateral asymmetries, and movement speed levels, indicating the quality of body movements. For future work, we aim to deploy the system to assess people living with chronic pain in real-life settings, which has the potential to replace the current intrusive on-body sensing technology with device-free Wi-Fi sensing technologies. Thank you very much.